Hello and welcome to another podcast. I believe this is podcast number 25. We're starting into thermodynamics, and reality is we're pretty much going back and rehashing a good amount of your second semester G-Chem experience. Things like energy diagrams, rate laws, Hess's law, bonds broken minus bonds forms in terms of energetics. And we're going to apply them specifically to OChem molecules and maybe an occasional biochem molecule. But the basic gist, thermochemistry is the study of energetics involved in chemical reactions. And so for delta G, we think about it, how favorable it is, depends on how much energy it releases. How unfavorable it is, requires how much net energy you must put into it. But also there's heat energy, the enthalpy that we look at. So how much heat energy or useful thermal energy can be released from a reaction, or how much you need to pump into a reaction to make it go. And entropy we'll look at a little bit. That's far more G-Chem topic and biochem topic. We don't worry about entropy that much. We'll look at it minimally. But our big thing in OChem will be looking at energy diagrams and making predictions about reactions. So we want to start with that. We have energy on the y-axis, and this can be either thermal energy, delta H related, or it can be just Gibbs free energy, delta G related. But according to this diagram, you have reactants. Reactants come together and they form some sort of transition state where they've starting to form a new bond, starting to form whatever product they're going to get to, and then it proceeds and forms those products and releases the energy from up here to down here. Notice that we call the x-axis the reaction coordinate. So we could say time, I think, but let's figure out what would be right or wrong with that. So time-wise, we start with reactants, go to transition state, and finish with products. So it seems like time should be just as good an axis, but no matter what book you look at, they always put reaction coordinate. And the reason they do that, the reason they don't say time, a reaction can go backwards. A reaction can go from reactants to products, products to reactants, and so forth. Time just marches in the forward direction. You cannot go backwards in time. And I'm sure you wished you could at different moments. The unsend button would be very nice and so forth, but you can't go back in time. But you can go back according to the reaction, hence called a reaction coordinate, the transition from reactant to transition state to product. And occasionally we might also see an intermediate in some graphs. How fast it goes, the kinetics of it is the upper portion. The net heat energy is the thermal portion. So again, kinetics, how fast, thermo, how much. We can also look at it in terms of activation energy. The activation energy is what you must put in. So from the start to the apex of the transition state. So that's your activation energy right here. That's this one here. And then delta G or delta H, again, depending on whether we're considering the heat energy or Gibbs free energy. If you're talking about Gibbs free energy, then this is said to be exergonic, energy releasing, meaning a negative delta G went down, or exothermic, meaning heat releasing. So if you touch it, the flask would feel warm. The exact opposite of that is endergonic, energy must enter the system to power it and make it go, or endothermic, heat energy must go in. So if you touched it, the reaction would feel cold. Convention is such that we always look at the chemicals. So what I mean by that is if the chemicals go from more reactive, unstable, to less reactive and more stable, they've gone downhill in energy, they have released energy, so we call it a delta G is negative, delta H is negative. Even though the surroundings, which is us, the world around it, feels the heat coming off, so we feel energy, so we're gaining energy as the environment. But chemistry, we're always chemical centric. We look at the system, not the surroundings. So one interpret energy diagrams. So the simplest one we just looked at is energy goes in, goes to a transition state and kicks out. Want to emphasize the fact that your activation energy is here, your free energy is there, just like we mentioned before. So there's your activation energy, the kinetic portion. Here's your free energy change or your energy release. So I'm going to make all these free energy diagrams. So this is delta G. Notice that the ends or the activation energy, what you need to get to the transition state, is greater than the released energy. So that's a safe reaction to be around. That means as the reaction goes, the energy it's giving off can't just immediately make another one go. And so if you look at the conditions for a reaction, if activation energy is really high, we have to heat it up. If it's medium, we usually do it room temperature, but if it's really low, we run the risk of this energy being so great that it can trigger another reaction. And eventually, if this is so much greater than activation energy, it can flood the system with enough energy that it becomes explosive. So if that's the case, we usually run those reactions at very low temperatures. We chill them, put them in some sort of liquid nitrogen ethanol slurry or CO2 ethanol slurry. The liquid nitrogen one probably couldn't work with, I'm sorry, when I said it worked with ethanol, we work with a low boiling point solvent. So we typically put something in there that doesn't freeze and doesn't boil away, so low numbers. Anyway, the point being, you have to run it at low temperature. Catalyst may help to make it go a little better, but if you add too much of catalyst, then you have to worry about the reaction going too fast. We also mentioned this one on the previous page, where it's highly energy investing to get it to go, and it's an unfavorable reaction. So delta G is a positive number in this case. You have to pump energy in. There's certainly unfavorable reactions we want to run, but usually to get some compound to turn into something else. We, as a general rule, try to run things downhill. But that said, if all reactions went downhill, then our world would run out of whatever we needed eventually, and that's just not the case. So energy is conserved. So there are some molecules getting more energetic as others are getting less energetic. Okay, this is what I was talking about, where the activation energy is very small and the delta G is massive, meaning if one reaction goes, it might be able to give you enough energy to do 1, 2, 3 more reactions. So 1 turns into 3, 3 turn into 9, 9 to 27, 8 to 21, or 27 to 81, 81 to 243, and 7 to 29, and so forth. I'm running out of my tripling ability, but in a very short amount of time, one molecule is turned into 729 molecules, and those are all racing out of control. So explosive reactions are typically designed this way: low activation energy and very large delta G. Is it an issue? I guess it's all in perspective. Need to blow up a mountain to build a road? It's wonderful. Try to blow something up that is of value to an enemy? Not so good. Probably not the best invention. You can ask the Alfred Nobel estate all about that. Okay, then there's this one. The start and finish look really, really close. So K-equilibrium, when it's just barely lower. So let's say I go here, straight line across. It's just a very slight drop. K-equilibrium for this one would be ever so slightly greater than 1. The problem with this reaction is it takes forever to go. So these are the type that you need to either heat up or add a catalyst. If I add a catalyst, I can make it more realistic. But a lot of our reactions that just churn over and make the molecule roughly the same energy can go back and forth and back and forth. So they usually end up in a multi-step reaction, just being an intermediate conversion here that I now have to take this product and push it further down the road. Okay, GChem review, unadulterated GChem review. So I'm going to go kind of fast on the assumption you've seen this already. And that is delta G is your free energy change. The terminology, negative is favorable, also known as exergonic and spontaneous. Delta G greater than 0, unfavorable, non-spontaneous, and endergonic. Delta H, exothermic when it releases heat, and then endothermic when it absorbs heat. And then finally, entropy, delta S. The world, it's favorable if the world falls apart. So if the delta S is actually positive, it's becoming more random. And that usually is favorable according to the equations, because positive delta S, because it's minus that, it becomes a negative delta G, which is favorable as far as reactions go. So if a reaction falls apart, it actually helps reaction to go. If it becomes more ordered, then it's a little less favorable, a little less random. So different things they like to do. They, being those who write chem textbooks, like to see what the scenarios are. So there's basically 4 combinations: minus plus, plus minus, minus minus, and plus plus. If delta H is minus and delta S is positive, then a negative number, minus, and T is always positive because it's an absolute Kelvin scale. So minus, minus a minus is even more minus. So in that case, delta G is always a negative number, always favorable no matter what. More realistic scenarios are when they're both positive or both negative. If this is positive and this is positive, then delta G can only be favorable if the T delta S is greater in magnitude than the delta H, So that's favorable when it's a high temperature, so T delta S is large, or where delta S is so massive. So if you have a solid turning into 9 million gas molecules, then that might be a case highly entropically favorable. So much so that it will overcome delta H. They're both negative. This is negative. Then you want this to be minimal because minus and minus is plus. So that'd be favorable at low temperatures. And then just like this plus or minus plus was favorable at all temperatures, if this is positive and this is minus, positive minus and minus is positive plus a positive, means it's never going to be favorable. Delta G will always be a positive number. Okay, so hopefully that rings familiar. So just to make sure we look at delta S, I want to analyze this. If I have two compounds, both with pi bonds, so their rotation within the molecule are about the same, and then a second molecule, the entropy is a wash. Two molecules going to two molecules, no changes in rings, no change in pi bonds. Delta S is essentially zero. So delta G equals delta H. I just look at the bond energy. So a lot of times we use them interchangeably if delta S is zero. However, there are some reactions. This is one you'll learn next semester called the Diels-Alder, where 4 electrons in a pi network react with 2 to form this cyclic system. You're going from 2 to 1 molecule, which means it's becoming much more ordered. So it's very unfavorable entropy-wise. So delta S is negative. So with something like that, a lot of times we have to heat the reaction up to make it go, to overcompensate or to compensate for that. Okay. So onward we march with this. Hess's law, hopefully, is one of those things that you've done in the past. So Hess's law deals with the addition of delta H's for a reaction series, or delta S's for a reaction series, or delta G's. So for delta H, what we're dealing with is overall reaction is delta H1 plus delta H2 plus delta H3, etc., equals the overall delta H. What you no doubt dealt with, I know for sure in 120, and probably even a little bit in 121, was products minus reactants. So if you have a certain amount of products that form, and you subtract the delta H formation of reactants, you're getting the overall delta H reaction. Don't want to go into too much detail with that, but just want to present that. And then I can also say delta G for reaction is summation of delta G products minus delta G reactants, or delta S, same story. So Hess's law, although I'm doing it for delta H, can also be used for delta G and delta S. Other rules, this becomes important. When you cut a reaction in half, the delta G, delta H, or delta S is also cut in half. When you double a reaction, delta G, delta H, and delta S are also doubled. So thermodynamic values take on the same rules as the reaction. So notice this one generated 120, or it required 120, it's positive. Whereas when I cut it in half, half of this going to one of these, it's only 90.25 now. When you reverse a reaction, so if I take NO and go to 1/2 O2 and 1/2 N2, then this becomes a negative number. When you run a reaction backwards, it's negative of what it was in the forward direction. And then finally, delta H is sum for all the reactions together. So if I add two reactions, so let's just take this reaction here, which we know to be 90.25, and add a second reaction, NO plus 1/2 O2 going to NO2. If I add these two reactions together, you'll notice NOs are going to cancel here and here. So NO's out of it. So it becomes 1/2 N2 plus 1 O2 going to NO2. It'll be the sum of those two. So it'll be about 33. So again, 1/2 N2, an O2, and NO2 gas, and around 33. This is just all old news. I'm not teaching anything new, so hopefully we get this out of the way. And then a little bit of math. This equation, delta G for a system starting at balance, one of everything going to equilibrium, gives what's known as the standard equilibrium. So the standard delta G, hence the knot, done under standard conditions of 25 degrees Celsius, 1 molar of everything, 1 atmosphere of pressure. So everything is nice and straightforward. The actual delta G you get isn't the standard, it's a standard plus whatever extra. So let me reword this. What it basically is the following. Delta G, what you actually observe, is from standard conditions, the middle 1, 1, 1, and 1 of everything going to equilibrium. That's this delta G naught, plus however much you're disrupted from the middle, the standard, if you will. So overall, if I want to go from start to equilibrium, I'm going to go from start to middle and then middle to equilibrium, add those two together, you get the overall delta G. This is not a math class for thermo, but just want to reiterate that we're going to worry about delta G, but note that delta G's can change based on where you start. So if I start really close to equilibrium, so let's say I started, let's just arbitrarily say equilibrium to middle plus middle to equilibrium, those are going to be exact opposites of one another. So negative and positive, or positive and negative, the same number, means delta G is 0. So if you're at equilibrium, no energy change, you don't move. If you move extremely far away from equilibrium, it's going to be more energetically favorable because you have this component plus this other component. This is just straight GChem memorization. Toss it in there because it's just a cool way to remember it. Q is where it's at. K is where it wants to be. So if Q is less than, or Q is more than K, K equilibrium is less than Q, then that means your product, your numerator is too large and your denominator is too small. So it needs to go from products, which is too large, to reactants, too small, which means it's going to shift backwards. So delta G for that would be positive. But an easy way to do it, totally true, but instead of doing this theoretical or conceptual calculation, I'm going to say just simply draw K and Q alphabetically. Here are K and Q alphabetically, and take this arrow, or take that greater than sign, just turn it into an arrow, meaning you do this. You draw it like this, which means it wants to go from products to reactants. When I turn the sign into an arrow. And then finally, we can plug in. It's RT ln of Q over K. So if this is minus RT ln of K, minus means divide. So this number divided by this number, RT ln is the common part. So it's all, this is numerator, that's denominator. So Q over K. So if Q is bigger than K, then big number over small number, log of a number bigger over smaller, log of a number greater than 1 is positive. So delta G would be positive. So all these predict the same thing. I like the alphabetical one, but if you like math relationships, log relationships, or you just like the concept of figuring out if Q is too big or too small, that will also work. Okay. This is taken from a certain standardized test. It's a release question, so I'm going to use this as a teaching tool. So I hope I do not ruin this question for you in the future, but this may very well have appeared on a standardized test of some sort. Assume the hydrolysis of ATP proceeds with delta G is minus 30 kilojoules per mole. So hydrolysis of ATP, definitely something you ran into in your bio classes, ATP plus water, and ATP plus inorganic phosphate. So just want to say right here and right now, biochemists say this wrong. You do not get energy from cleaving a bond. You don't get energy from breaking ATP. You get energy from the overall reaction that just happens to break ATP into ADP and PI. But it's the chemical reaction for the whole thing. So just want to correct that number way in advance. But for this one, which one gives the expression for the ratio of ADP to ATP? So we have to break out, our equation has RT in it, has a delta G because they gave that to us, and has a K equilibrium because that's the other thing in the equation. So K equilibrium is products or reactants minus the water. So no water in this. They told us that inorganic phosphate concentration is 1 molar. So plugging in a 1, that's just going to go away. And so K equilibrium actually reduces to ADP over ATP. So plugging in this for right there, we will get delta G equals negative 2.5 natural log of that, because they told me RT equals 2.5. So negative 2.5 natural log of that ratio. So I plug in a negative 30, negative 2.5, divide each side by negative 2.5, we end up with 12. Now the trick is to get rid of a natural log, you have to put e to the power. So e to the 12 will equal e to the natural log. E to the natural log cancels. So that simply means e to the 12th equals ADP over ATP. Lots of math. This is actually was considered an organic chemistry question on a certain standardized test. So the point of this being the topic we're doing, although you do it in biochem, you also do it in GChem, fair game for OChem as well. Okay, radiant K equilibrium delta G. I just want to give you a massive table of how these things connect. If you have a K equilibrium 1, your delta G is 0, because plugging that equation means natural log of 1 is 0, so it's got to be 0. You need your product ratio 1 to 1 on each side. One point of interest, my table is different if you happen to be looking at the one in the book, and the reason being, I believe the person in the book forgot to square what they have to do. So let's say, for instance, we have this number right here. If this is 3.1, and this is 3.1, and this is 1 and 1, it's going to be 3.1 times 3.1, or 1 times 1, which equals 10 over 1, which is that number right here. And then plugging in, natural log is negative 2.3 when you convert to log, so negative 2.3 log of 1 is just negative 2.3. So the point of it being, it really doesn't matter that much. The fact that they mess that up, don't really care. Just know that you have a certain favorability of product to reactant, but when you have two things, you have to make sure to square it. Okay, so I'm going to break the thermo into two portions and then kinetics into one portion. So this is going to be the first of 3 podcasts for the thermo and kinetics associated with this. So I hope this is going well so far, and we will catch you at the next podcast. So see you soon.